Hey, good afternoon, everybody. I'm very pleased to have Qian Yuan here. I ran into Qian on the Caltech campus about 6 months ago, just about 6 months ago, and he was about to submit a paper that sounded really interesting and provocative, and I invited him to come and talk to us about it. That paper has since been published. So Qian is, he comes to us from long ago from Wuhan, somewhere near Wuhan, the famous place in China. And he grew up around there. He went to Wuhan University for his undergraduate studies in geosciences. And then he came to do graduate studies to our sister institution at the ASU in Phoenix. So he finished up there about 2 years ago, and now he's a postdoc, the OK Oral postdoc fellow at Caltech in the geoscience, what is it called? GPS, geosciences and planetary sciences, geological and planetary sciences. I should know, I used to be there. And today he's going to tell us about this very interesting, and I said kind of a provocative idea that he has about the ancient Earth and Moon. Take it away.
Hello. Can you hear me? Hello. Hi. Yeah, okay, thank you. Thank you again, Renu, for the invitation. It's my great pleasure to come back. I stay in Arizona for 4 years. I really miss the time, now summer, but this is the best time. Good to see you all. Okay. So the title is Uncovering the Buried Planet That Formed Our Moon. So I know this is kind of late. If you really hurry, this is the image that you want to see. This is the buried planet I was trying to propose. There are two of them. One is beneath the Pacific, one is beneath the African continent. I propose this blob may represent part of the moon-forming giant impactor. Okay, so that's very short summary. But if you know how this formed, because this time scale happened 4.5 billion years, this is the current Earth. If you want to know how that evolved, please stay here. Okay. First, I want to thank my collaborators and supervisors. Without them, I cannot achieve this. And particularly for my PhD advisor, Mimi Li, Edward Canero, my postdoc advisor, Mike, and also Paul. And also, if you are interested in any part of my research, feel free to show me an email. So yeah, so here is LPL. So I think everyone here knows moon better than me. But let's first look at the moon. So this is a famous image. Probably everyone here have seen this image. Here is us, this is Earth. So we didn't see the moon, yeah. But let's zoom in, yeah. As you can see, this is our moon. Actually, this is the first image of our moon and Earth together, taken from the outer solar system. So that suggests our moon is so large that it can be even seen even 1 billion miles away. And since most of people here have a strong background in geophysics or physics likes numbers, let's look at the numbers. So in terms of mass, as you can see, our moon's mass compared to Earth is larger than 1%. It's way, way larger than any moon in our solar system. So Mars is the only other rocky planet in our solar system. It has two small, tiny moons. Together, the mass ratio compared to Mars is 10 to the negative 8. So for Ganymede, it's the largest moon in solar system. Compared to Jupiter, it's only 10 to the negative 5. So you can see, according to numbers, our moon is anomalous large. So at least 1,000 times larger in terms of ratio compared to its host planet. Then everyone should be curious about the origin of the moon. And I think everyone knows this. This giant impact hypothesis for the moon's formation has been proposed more than almost 5 decades ago in a conference in Cornell University, I believe. And when I give this presentation, Dave Stevenson told me he was right in that workshop. I was so jealous. He said he was a graduate student at the time, 50 years ago. It's fun to know that. So this giant impact idea has been more and more accepted in the last few decades, and because it can explain three fundamental characters of the Earth and Moon system. First is that in the canonical moon-forming giant impact, this has been numerically tested by Robin and Eric from here, like more than 2 decades ago. So after that giant impact collision, where the impactor is Mars size, it collected with the Earth about 45 degrees. After that collision, the Earth and Moons will have angular momentum that match the observation. That's the first one. The second one, as you can imagine, these two planets already differentiate their core. So the collision will be mostly involve their mantle. So in that way, most of the materials forming the moon come from the mantle. So that can explain why the moon's core, why it's very, very small. So less than 2%. For comparison, Earth's core mass is about 30%. So you can see how small for moon's core. And also because this collision involves such a strong energy, so many of rocks and vapors and rocks are vapored or melt. So a lot of gas were related during that processes. So it can also explain why the moon's volatile is strongly depleted compared to Earth, although Moon and the Earth have similar isotope, as I will touch on later. And also for this canonical moon-forming giant impact, for the mass and the size, and also the velocity angle is pretty common in planetary formation model. So this is why this canonical giant impact scenario has been more and more accepted recently. So, but this canonical model has met a lot of significant challenges in the past more than 10 years. Yeah, about 10 years or so. So it was suggested by Jim Malash, and it's called most isotope crisis in canonical model. Because from Apollo, we measure sample and we have lunar meteorites. We found actually the Earth and Moon have a very, very similar, almost identical isotope for many isotope systems. But according to canonical giant impact, more than 80% of the materials making the Moon come from impactor theory. If you consider these two evidence, that will require the impactor theia and the proto-Earth have similar isotope. But that is very, very small possibility event according to planetary accretion model, because for large planetary bodies, the possibility for them to have similar isotope is very, very small. It's less than 1% in some papers. So this is called the most isotopic crisis in canonical models. So because of that, in the past 2 decades, there have been proposed non-canonical giant impact models. There are mostly 3 kind of scenarios, new scenarios. They are non-canonical. First is called hit and run models. So in these models, so impactor hit on Earth, and then part of the mass escape from the system. Another one is called fast spinning Earth. In that way, the Earth rotates very, very fast. It becomes almost unstable by itself. So in that way, you have an impactor, so they will make Earth even more unstable. So it will release more materials from the Earth to the orbit. So that can explain the isotope similarity between the Earth and Moon. So the recent one getting more popular is called the high energy and momentum, and also high angular momentum and high energy impact. So there are two scenarios. One is half Earth proposed by Robin, and also this Celestial model proposed by Simon and Sarah. So basically, all these 3 models involve higher energy, and also all these 3 models will end up angular momentum that's slightly higher than the Earth and Moon system, which is not required in the canonical giant impact. And also, particularly for this high angular momentum and high energy impact, the energy is so large, it will melt or vaporize almost all the mantle for these two planets. So that way, it will lead a lot of mixture and will homogenize the Earth and the Theia. So it will lead to a basically a simplified homogeneous Earth. So most of the people here are from planet science, but I'm mostly an Earth scientist. There are so many observations required that Earth is not a homogeneous Earth. There are so many heterogeneities, and some of the heterogeneities are very, very ancient. So Earth is not a perfect layer. So in that way, these three models are not very consistent with observation on the Earth. And also they have a different angular momentum compared to the canonical model. So then what's the solution? How to trying to answer that questions? So 4 years ago, I don't know the giant impact origin for the moon. So, but I have this idea is that if you don't know what's the chemical signature of Theia, how could you know whether moon is similar to Earth or Theia? So I have a daughter, she's 20 months old. When I take my daughter to the park, people nearby will say, oh, your daughter looks like exactly like you. The next time my wife took my kid to the park, people say, oh, you are just another version of your mom. But you won't be able to tell whether your daughter looks like you or your spouse unless you find their both. So that's just my feeling. So then the question is that, where is the missing impact Theia? So this is a question proposed by my professor while I was taking class at ASU. That's really sparked me to have this idea. We don't find the remnant of the Theia in the asteroid belt or in the meteorite group. So then where is it? I was wondering, could it be, we don't find it at the surface or in the other part of the solar system. Could it be in the interior of the Earth? So that's my guess, because at that time I have been studying the Earth's interior for a year. I know there are two large regions in the Earth's interior. I know they are really large. So that's my hypothesis right in the class. So after that, I spent a few years, quite a couple of years, to continue that project, and we demonstrate that's possible, at least in our models. So that paper was published just in November, the beginning of November. So those are the two blobs sitting at the Earth's command boundaries. So we propose these regions have been seismically reviewed as large, low shear velocity provinces, and I will just simply call them mantle blobs. So I argue in that paper, these two blobs may represent part of the missing moon impactor's mantle after 4.5 billion years. So in the next 30 minutes or so, I will try to convince you this is not a lunatic hypothesis, but it's also lunatic because it's related to the moon's formation. Okay, so before that, because most people here are planetary background, I will give some background on seismology, because this is the most direct way we can see the interior of the Earth. So in seismic tomography, this is a technique we see the large scale structures in the interior of the moons. So we are particularly interested in two colors, actually, one blue, one red. In every seismic data image, so these are the two important colors you probably want to know. So blue represents fast velocity. Usually they are related to subtectonic slab, because in Earth we have this unique mantle convection mode called plate tectonics. We have subduction slab can subduct and beneath the surface and reach the lower mantle. So these linear slab structures beneath our feet here, cross section shown here. So blue means fast anomaly. Usually they are related to slabs, subducted slabs. Another color is red. Red means slow velocity. Typically, the temperature is hotter than the rest of the background mantle. So you are probably famous with Yellowstone. Yeah, I haven't been there, but I wish I could go. So here is a cross section beneath Yellowstone. You can see this is a command boundary, by the way. This is also command boundary. So you can see there are red plume-shaped structures rising directly from the chromatic boundary towards the surface beneath the Yellowstone. So those I showed basically for the cross sections to help you understand what's blue represent and what does red means. So one blue means fast anomaly means slab. So red means plume structures. Now let's look at the global seismic tomography. This is a cross section of the whole Earth. So you will see there are some a lot of regions are white. These are just background mantle, similar to the yellow in the previous slide. So let's focus on blue and the red. So you can see a lot of blue structures. These are slabs, and this can be accumulation of subducted slab. These slabs are denser, but you will notice there are two large, massive red blobs. These two blobs doesn't look like mantle plumes as I shown before. So those two blobs are massive. So what are they? So those are called large low shear velocity provinces. When seismic wave travel through the interiors, we found in these domains, the seismic wave travels slower than the background mantle, usually about a few percent slower than the rest of the mantle. That's how Earth scientists can image them. So one is beneath the Pacific Ocean, one is beneath the African continent. So they are not only shown in shear wave velocities anomaly, but also share in P wave, compressional waves models. As we shown here, the green show the P wave models. So also degree 2 structures, one beneath the Pacific, one beneath the African continent. So these 2 degree 2 large structures are consistent in every global seismic tomography. They have been found more than 3 decades ago, but usually people think they are formed by Earth's internal processes. So as I just mentioned, they have been found by decades. So since they are located in the deeper part of the Earth's mantle, and also we know the Earth have subduction slabs. So the first popular idea for the origin of the blob, namely, is that they form by accumulation of subducted ocean crust. Because subduction ocean crust have a different chemistry when that enters the Earth's mantle, so it becomes denser. So after billions years of accumulation, in principle, you can accumulate a large blobs by time. But the problem for that is that ocean crust, the thickness is only 6 kilometers. So this is a slab. Slab in the lithosphere is a thickness usually about 100 kilometers in thickness. But only the crust material, the green material, can get separated about the chromatic boundary because that's the part have a higher density. So that's very, very small. So my PhD advisor's PhD focused on that. His model show that it's almost impossible to form such a large scale structure only by this crust because this crust are very, very small. So it's hard to form these large scales just by that. Another popular idea is form this mantle blob may form by basal magma ocean. So this paper published by Steve in 2007, also in Nature, it's very popular. So that paper assumed in the beginning of Earth, we have a whole depth magma ocean. Yeah, basically, probably after the giant impact. That paper didn't do any giant impact simulation, but he assumed there's a whole depth magma ocean. So in that way, because the liquidus is close to liquidus of the sentinel rods close to the adiabatic at the middle mantle. So in that way, it will start to crystallize from the middle part. So in that way, you will crystallize towards the surface and towards the bottom. So in that way, you will end up with a basal magma ocean above the Earth's chromatic boundaries. And also iron is a strong incompatible element. So that means iron will prefer to stay in the liquid. So when this magma ocean solidifies, so this solidified part will be relatively iron rich compared to earlier mantle. So yeah, this is a very popular idea to explain the formation of this blob. But as I mentioned, this model haven't done giant impact in their simulations, and we are not sure at the beginning of the Earth's evolution we have a whole depth magma ocean. So also I have to say, a purely thermal origin for this blob is not excluded. It's still possible, but the majority of the people in our field think these 2 regions, this mantle blob, require a different chemical and the chemical composition than the rest of the mantle. And why we study LCPs in earth science? Not only because they are large, so I think I missed one slide. So each one of the blob is comparable to the mass of the moon. So as you can imagine, they are really massive. And those two blobs are the largest mantle heterogeneity in the whole mantle. And also earth scientists have found that in the past 200 million years, as you can see at the edges of these mantle blobs, the majority of the large igneous provinces and also hotspot volcanoes and also kimberlite eruptions, those represent the largest volcanoes in Earth's history. They seem to mostly occupy at the edges of these blobs. So there is some correlation between that, and we still don't know why. By saying that, I'm saying that by studying these LSPs or mantle blob, we can in principle understand Earth's long-term thermal and chemical structures and evolutions as a whole. Okay, so let's see the time. Okay, still good. So in the following presentation, I will give 4 major evidence to demonstrate it's possible that part of the impactous mantle form these blobs after 4.5 billion years. So first, I will just show here. I will show this is a real data, seismic data for this blob. As we can see here, there are 2 of them. There is a variation for the total mass of the blob, but even the lowest estimation is about 2% of the whole Earth. So as you can see, in that way, it means at least each one of them is comparable to the whole mass of the moon. So for the largest end member is about 6% of these 2 blobs. So it's comparable to about 75% of the mantle for the real Mars. So actually, this was the first thing I checked after that class. I just want to know if they are comparable in size. So as you can see here, these 2 blobs are really massive, but you definitely can't just doing research by comparing numbers. So in the past two years, we have run real giant impact simulations with my collaborators. So here we are running a canonical giant impact simulations. Here is the impacted Theia, it's Mars-like. Here is a proto-Earth. The color here represents entropy, which is similar to temperature. So let's focus on Earth's mantle. It's green before the impact. Now let's see how the color change after this giant impact. As you can see, collision most happen on one hemisphere of the Earth. The other hemisphere of the Earth is less affected in the first few hours, but the Earth is keep rotating and there is a later heat. But you can still see a large hemisphere of the Earth kind of remain green during these processes. And after this is a time in hours. As you can see, after 10 hours or 20 hours or so, the system reach almost steady state. So you can see there remain a green layer above Earth's core mantle boundary. So that's the Earth's lower mantle. That suggests this canonical giant impact didn't melt the whole mantle. It should melt the majority of the upper mantle and vaporize most of them. But Earth's lower mantle can remain most solid. So this hasn't been shown in previous model. And actually our work is the first to show that a canonical giant impact didn't melt the whole Earth. It only melted half of Earth's mantle. So why previous work didn't show that? One of the reasons is that we use a very, very high resolution. So one of the simulation we use is by Swift. Their model resolution can be 1,000 times higher than previous model. So, and also we explore different results. If you use low resolution for SPH, you will create more artificially viscosity. Then it will lead to more artificially heating. So that will lead to more melting. When you start to have high resolution, you start to melt less and you form these 2 layer structures. And also the result will confirmed by another code by Gizmo. It's not SPH, it's called meshless method. It's also consistent with the other model. And also we use a very recent equation state published by Sarah Stewart a few years ago. It's more accurate. in my opinion. And also, we have run more than 10 of these 3D giant impact simulations, and we tracked how much fraction of the impactor's mantle can directly enter the Earth's solid lower layer. We found their mass is about 1 or 2%. So you can see these small red blobs, they are randomly distributed in the Earth's lower mantle. Their mass is comparable to the mantle blob we see right now, although they are in a completely different shapes, but their mass initially, they are comparable to each other, about 2%. Okay, the second evidence we collected is from geochemistry or cosmochemistry, because in order to demonstrate our hypothesis is possible, we require this blob to be denser, to have a higher density than the rest of the mantle. Otherwise, with whole mantle convection, it's likely to mix together. And for every silicate rocks, iron content is the most important parameter because iron is a major element, it's a densest major element. If you have more iron, it will be denser than other silicon rocks. So for Earth, for the bulk silicon of Earth, the FeO content is well constrained, is less than 8%. For the Moon, the bulk silicon composition of the Moon is still debated, but right now in the literature, even the lowest estimation is larger than 11%. So this is kind of interesting. If the Moon was made of a mixture of these two planets, how could the Moon have higher iron content than the Earth? So because of mass balance, I think the most straightforward explanation is that you would expect the impactor's mantle is more iron rich. So the mixture of the moons can have an iron content between them. So this is our opinion. And also is supported by previous work, cosmochemists and geochemists. And actually previous people have run different kind of scenarios to consider the FeO content for proto-Earth or Theia. In this study, the x-axis shows how large fraction of the moon come from Theia. So here you can see this is a canonical model. This is hit and run, also high energy and angular momentum. In all these different scenarios, you will see that Theia's mantle have higher FeO than Earth or proto-Earth in all of these scenarios. This kind of makes sense because of mass balance. You require Theia to have higher iron content. So built on this model, so our collaborators, Steve Dash, considers a recent measurement of hydrogen isotope on the lunar meteor Apollo samples. So he further refined the FeO content of Theia. In his study, he suggests the Theia's FeO is about 13 to 18%. It's about twice FeO content compared to Earth. Still smaller than the real Mars, but it's twice higher than the Earth. So we'll use this FeO content for Theia, and we'll use Mg and silicon ratio to 1 and to estimate the chemical composition of Theia, and we'll compare that with the bulk silicon composition of the Earth. The x-axis here shows the pressure, which is the depth. The y-axis shows the density anomaly, density difference of Theia compared to the Earth. So we have 3 cases for the Theia's mantle, 13, 15, and 17. So as you can see in these scenarios, all these Theia's materials will be denser than the rest of Earth's mantle. They are about 2% to about 3.5% denser than the Earth's mantle, slightly denser than the Earth's mantle, not crazy high. So this density anomaly is a parameter that I'm going to use in our mantle convection simulations. So far I have provided 2 evidence. So we have run giant impact simulation. We showed this impact didn't melt the whole Earth, and also 2% of impacted mantle can enter the Earth's lower mantle directly. They form as random blobs in the Earth's lower mantle. And also we can, based on geochemistry and cosmochemistry evidence, we infer this red blob has higher FeO content, which means it will be denser than the rest of mantle. So in the next part, I will run mantle convection simulation to show how this small blob will sink and survive Earth's 4.5 billion years and end up with two blobs as we see right now. So I'm mostly a geodynamicist. So we use supercomputers to solve three fundamental questions: conservation of mass, and momentum, and energy. So, and we will use different rheology, based on your different research problems. If you are interested in long-term, large-scale, particularly lower mantle problems, you will want to use viscous flow because viscous creep is accepted rheology in the lower mantle. If you study some lithosphere and shallower processes, you want to consider elastic and brittle failure as well. So it really depends on your model. And of course, we use supercomputer. Can also for some simple 2D model, you can use your laptop. But most of the time, you use supercomputers to solve these models. So here is the setup for the model. This shows the compositional field. We put some randomly distributed Theas blob. This blob total mass about 2% we constrained from giant impact simulations, and we give them a higher density because of the geochemical consideration. They're about 2.5% denser than the rest of the mantle, and we use a temperature dependent viscosity of course. So here is the same field. This shows the composition. This shows the temperature field. We use a relatively hot temperature in the early Earth. So this start from a short time after the moon formed giant impact. Yeah. So let's see how this model goes. So as I mentioned, this initial blob are denser, so they will quickly sink down to a Kuhlmann boundary in tens of millions of years. So, and we can see there's a blue structure, they are subduct slab. So subduct slab will keep shaping this mantle blob. So sometimes we'll separate into three, sometimes it will merge into one. And you can see there is mantle plume keep rising from the top or edges of these mantle blobs. So after 4.5 billion years or so, we end up with two blobs, massive blobs. And the total mass are comparable to the mantle blob we see in the Earth right now. And we see there's strong plume rising from the top of them. So this is just a reference case. It's 2D, but we confirm by using different Rayleigh number. Rayleigh number is a factor measuring the convection vigor. And also we change the density range that constraint in the second part. It doesn't affect much. And also we use different rheology and also can still have the similar results. So also, since this is the model, we have everything we need. We have the pressure, temperature, composition in the second part. So that means we can calculate the seismic velocities within these regions. So here show the result of the seismic velocity regions, velocities in this region. We found within these regions, there are indeed a few percent, the seismic waves velocity are indeed a few percent slower than the rest of mantle. And also the size about 3.4% volume compared to the Earth's mantle. All of these are very, very comparable or consistent with the observation from seismology. So this is all successful model. Of course, we have some bad or failed model. The model doesn't fail, it just didn't produce the result we want them to have. So this model, we have a smaller radius for these small blobs. So in order to have the same mass, we have to have more numbers of these small blobs, but it have a smaller size compared to a reference case. So in that way, let's see how this movie goes. So here is the temperature as well. This is the composition. This shows the viscosity. So let's see. Because they have a smaller blob, so it's kind of relatively hard for them to sink, but still majority of them can sink quickly. But still, there is a more mixing for these small blobs with the Earth's mantle in this case. And about 2 million years or so, you can see the volume of this blob reduced a lot. And after 3 billion years or so, you can see it could become less and less because of entrainment with the Earth's mantle. And after 4 billion years or so, yeah, you don't see this large blob in the Earth's mantle. Yeah. So this is the field case. Yeah, of course. Yes. So, but there's always a trade-off between the initial size of the blob and also the density. Because in the second part, we estimate there is a density range for this blob. If you use a slightly higher density for this smaller blob, it can still produce this blob can still survive, as I will show now. So this animation have the same setup with the previous field result, just except that this blob have slightly higher density than the previous one. So you can see in this case, it become more stable because of the higher density. And for some of the time, you have a global layer in the first 1 billion years or so. But around 3 billion years or so, it kind of separated by this subduct slab. It still end up with two large pile of blob structures. And also there are plume rising from the top of it, and still comparable to the mantle blob we see right now. Okay, so right now I have provided 3 evidence, the joining pack, and show they have a comparable size for this TS mantle compared to this blob, and also we show this blob may have a higher density than the Earth's mantle, and then we use a series of mantle convection simulations to show this random blob can sink and survive Earth's whole history. And but all these are based on some assumptions, and on physical model or giant impact model. These are all based on some assumptions. The problem is how to test that idea. And also we are also very interested to know what's the age of this blob, because my model is right. That suggests that the blob should be very, very old. So in that way, we have to know some chemistry and also geology problems. As I mentioned earlier, in the past 200 million years or so, we found there are strong plumes. They seem to locate at the edges of these mantle blobs. So in principle, mantle plume can bring some chemical signatures from this blob and rise to the surface and cause some ocean island basalt or large igneous provinces that can be measured by geochemists. Because this is the only way, because we can't now get sampled by us directly, but with these strong correlations, so it's possible to say some mantle plume. And also in my animation, you will see there's strong mantle plume keep rising from the edges or top of this blob. So in principle, it may bring some chemical signature to the surface that can be measured. So a professor in UC Davis, Sudrai, actually measured one of these ocean island basalt from Iceland. It's very, very close to the African LSPs. So his study found that in the magma source of Iceland mantle plume, there is a very distinct and primordial neon isotope signature compared to mid-ocean ridge basalt, which represent the Earth's normal mantle or upper mantle, average Earth mantle. There's no mixing at all. So that suggests this reservoir, this signature, primordial signature, have remained isolated with the Earth's mantle for Earth's whole history. And also because of this neon isotope, this anomaly can only be formed in the earliest history of the Earth. So that suggests if this mantle blob are part of this, is the reason for this signature, that suggests the blob should be very, very old, even older than the age of the moons. So it's consistent with our physical model. So that's one evidence. Yeah, of course, Iceland is one example, and also for some other plume around these blobs, people also found some other evidence, also noble isotope. But how about signature on the moon? Because if our model is right, in principle, we may also find some signature on the moon as well. But remember, noble isotope is very, very hard to measure. So only 2 years ago, we have the first paper studying the noble isotope on the moon. So the title is called Indigenous Noble Isotope in the Moon's Interiors. In the discussion, it said the primordial light noble isotope in the moon detected in their study are similar to those in the Earth's mantle. And also is a solar type neon isotope, and about 13, in terrestrial mantle plume. that's likely sample the deep reservoirs. This signature is comparable to their lunar neon isotope measured in their study. So their result will plot in this region. So this is very, very interesting to me. So that paper was published before my paper. So in that paper, they didn't say anything about Thea. But according to my model, I think that totally makes sense. Because why? Because if the giant impact hypothesis is right, Moon must sample 2 planets. So that means in the interior of the Moon, we should find another different isotope compared to Earth. And in the Earth, we know, as I mentioned in the very beginning, Earth is not a homogeneous planet. They have heterogeneities everywhere. And even for large scale, 2% or 3% large scale heterogeneities. And as I mentioned, strong mantle plume may sample this blob and give rise to the large igneous provinces and hotspot volcanoes. They already show a different noble isotope compared to the Earth's upper mantle. So, and that study found a similar neon isotope from the lunar meteorites, which is comparable to the signature we inferred from the Earth's lower Earth mantle blobs. So, because after formation of the Moon, we shouldn't expect any material exchange from the Earth's interior with the Moon. So the only possible relationship possibly come from the giant impact, come from the impact of Thea. This is my kind of interpretation for their data. But I definitely look forward to have more lunar sample, particularly from the lunar mantle sample, to further confirm my interpretation. So, okay, so let's go to the beginning, the isotope crisis. Our study also have some implication for that as well. So if my interpretation and model is right, so we will infer that the interior of the Moon may also have some Theas-like signatures in the interior of the Moon. That signature may be very similar to the mantle blob we see right now in the Earth. So in the Earth, mantle plume can bring part of the signature to the surface. So by that, how to reconcile the Moon's isotope crisis? So my interpretation is that it's possible only the measured lunar samples, are similar to Earth's upper mantle, not the Earth's whole mantle, because Earth's lower mantle are very heterogeneous, particularly for this large-scale structure. And even for the Earth itself, it's largely homogeneous. So that's my kind of interpretation as well. It helps a little bit to reconcile the isotope crisis. But of course, it's also worth to explore more in the future if we can get more samples in the future as well. So in that, our study provides 4 evidence to connect the current Earth observations with the first major event happened in the beginning of Earth's evolution, about 4.5 billion years ago. So by that, so our study has a lot of implication to understanding the large-scale geological tectonic processes happening in the Earth. Because in the first 600 million years, we don't have any rocks in the Earth's surface. So it's hard to reconcile many things. But if we know this blob have been staying in the Earth, they may play a role in the surface tectonics and the supercontinent or other things. So in the following 5 minutes or 6 or 7 minutes or so, I will provide some ongoing work for this study. I will focus on this subduction problems. So, sorry, I have water. So, a question, yeah. Do everyone know subduction plate tectonics? Okay, good. I gave a talk in high school. I have to explain what is plate tectonics. It takes some time. It's very hard to explain to them. Okay. Subduction is a driving force in plate tectonics. That's the most crucial part. And Earth right now is still the only planet, rocky planet, have plate tectonics. But we don't know why. So there is a chicken egg problems. If you have a weak zone and plate boundary, it's very easy to form subduction. There is no doubt about that. There are 10 ways have been suggested you can form subduction if you have a weak zone or plate boundaries. But the problem is that if you don't have a weak zone, you have a single piece or lead, stagnant lead convection. That means the whole lithosphere is a lead. How to break it and start the first subduction is a key for subduction initiation and plate tectonics. So right now, there are 2 ways to generate subduction without weak zone. One is by large impact. If you have impact size like 1,000 kilometers inside, it can break the lithosphere and induce subduction, as you can see here. But in this paper, this subduction is short-lived. It will disappear quickly after 2 million years because it needs the large-scale impactor to keep bombarding the Earth to make it happen. And also, we know for this kind of large impactor, it's kind of rare, even in the Earth. Another one is internal driven processes, endogenic, plume driven. If you have a large plume beneath the lithosphere, it's in principle, it may break lithosphere and induce subduction. This paper has also been published. But the problem is that in the early Earth, the temperature should be hotter. So that means the viscosity is relatively slower. So that means the plume it's hard to form large plumes. So then I was wondering, could we have a hybrid model that can combine this together? So yeah, I get a solution for that. I consider the giant impact and also the giant impact remnants. So in this way, you have, after you have the giant impact, you form a layer structure as I suggested previously. And then you have some TS mantle, you will form some layer, pile structures at the bottom of the command boundaries. And from geological observations, we see that mantle blobs are related to strong mantle plumes. So I was wondering if this blob forms such early time, could the strong plume rise from the top of this blob and give rise to the first subduction? And also this blob has remained in Earth's interior for the Earth's whole history. So that means it will keep releasing strong plume when it's moving around. So that can completely change the surface tectonics thing, and also may help to initiate plate tectonics. So that is a hypothesis. So I have run this paper, it has been in revision. So here I show a 3D models. This is a regional 3D model. I put the TS mantle blob sitting above Earth's command boundary. So here model, I use a very strong temperature-dependent viscosity. The viscosity can vary by 6 order of magnitude. So in that way, if I remove this material, it will end up in a stagnant lead convection. It won't have a subduction, won't have subduction. So let's see how this model goes. Okay, so because these are strongly heated by Earth's command boundaries, you will see a strong plume can be generated quickly from the top of this block. And then you can see the strong plume can go to the surface and break the lithosphere and induce subduction around the plume head. So it takes about 100 million years, but there is because of the giant impact for the surface part, you still have the magma ocean, and we don't know how long it takes time for the magma ocean to solidify. So we give them like 50 million years to assume you already have a protolithosphere. Then the plume can rise and break that lithosphere and induce subduction in about 100 million years or so. So in that way, this model can combine the previous 2 hypotheses together. We only have one giant impact, which is a moon-forming giant impact, which is very likely. And another one is, since you introduce this mantle blob, it will produce and release these strong and mantle plumes. Also, the subduction can form some silicate rocks melt and go into the surface. So that can explain some geochemical signatures found in West Australia. They call Hayden digital zircons, and they are about 4.3 years or 4.4 years or so. Some geochemists measure those grains and suggest at that time, in some part of the Earth, there may be some regional subduction already at that time. So our model is consistent with their observation. Okay, so it's also our model has some implication to understand the diversity of other rocky planets as well. So Mars is another planet, have moons, 2 small moons, has surface dichotomy, and also Mars has the largest volcano in the solar system. So so I was so it's possible that the interior of the Mars may also have some heterogeneity, and that heterogeneity may be also created by the giant impact processes. That's something I want to do in the future. For the Earth, of course, it has a lot of implications to understanding the large-scale processes within the Earth's history. Of course, if you want to relate this blob to the surface observations. For the Venus doesn't have a moon, which I think is quite a big difference compared to the Earth. But Venus have these corona structures, which are being formed by plume, but this plume may be thermal plumes, not like Earth plume rising from the blobs. So this may be a difference between the interior of the Earth and Venus. And for Mercury, it has a very large core. People have been suggesting it may be large impact has stripped off most of the mantle. So as you can see, giant impact and considering the long-term effect of the giant impact may really help us to understand some large-scale tectonic geological feature and structure of these 4 rocky planets. And using some of this idea, I secured 0.8 million in the past 2 years, and hopefully I can get more in the future. And in terms of habitability, I think also is very interesting because of liquid water and also atmosphere and plate tectonics are 3 very important factors for Earth's long-term habitabilities. So interesting, I found that giant impact has been suggested as a potential factors to lead that, such as some geochemists are arguing that giant impact may bring water to the Earth. So that's why we could have water and ocean. And also during the giant impact processes, the core merging together. So that will change the core composition. So later on that chemical signature injected in the core can get out from the core and also can help to drive the earliest dynamo in Earth's history, suggested by Joe and also Dave a few years ago. And our study suggests it may generate the largest mantle heterogeneities and also give rise to strong plumes, which may be the reason why Earth have subduction and plate tectonics. And given such an importance of the formation of the moon for Earth's evolution, so I'm really surprised to know that there is no confirmed exomoon so far, although we have thousands of exoplanets. So I think, if some of you are astronomers or you have friends are astronomers, please, encourage them to keep looking for exomoons. I know it's very, very challenging, but in my model, I'm trying to say large moon is very important, not small moons. So the larger, the better, from my understanding. So hopefully in the next decades or sometime, we can have some exomoon being confirmed. That may be helpful to find another Earth, in my opinion. So 100 years ago, so after Wagner proposed the continent can move horizontally, it was thought lunatic or crazy at that time. It took scientists a half century to realize that's a real case, and right now every people agree with that. I don't know how many centuries my idea can be tested or confirmed, but I definitely am interested to explore this model further to trying to unite the Earth and planetary science together, because as long as we are still living in this planet, Earth is still the unique planet to many of us. Thank you.
And we'll take questions.
Sorry about that.
Thank you. Results. Thank you. I was wondering for your thermal convection Prandtl number in the simulations.
Reading number?
The Prandtl number.
Oh, so in orbital convection, we use a reading number. Reading number have some relationship with that. Reading number is about 10 to the 7. It's an Earth-like number.
What about the Prandtl number, which describes the inertia?
We didn't consider that.
Oh,
we didn't consider that because mantle convection is very, very slow. It's on million years of scale. It's very, very, very slow. We didn't consider that in our mantle convection models.
And so, how do you how do you consider the interaction between the molten part and the solidified?
Oh, nice question. So in all these models, so because magma ocean is very hard to model and very large scale, really number will be super pretty high. And also you will need to solve equation for different solid and melt together. So all these matter convection are based on solid state matter convection model. We in the first part, so I have to say that let's see, even you have the whole depth magma ocean. So there is agreement that solidification of magma ocean is very fast, usually finish within 50 million years or 100 million years is definitely enough to solidify all the magma ocean. So we will just start our matter convection from that point. From that point, we don't want to deal with that magma ocean stage because that stage is very dynamic and very hard to constrain, but also it's a very short time period compared to Earth's 4.5 billion years. It's largely driven by solid matter convection processes. Yeah, but if you are interested in the surface structures in the first 200 million years or so, but I think it will be important to consider that effect. Possibly you want to use multi-phase flow to do that as well. But right now, in my knowledge, there are many simplifications and you cannot study a global scale, probably regional, yeah, very, very regional scale. Thank you for the question.
Yeah. Oh, great. Fantastic talk. Thank you.
Thanks.
I had a question actually now that we're at these slides. Can you discuss a little bit more this slide and the two before you were discussing the difficulty of getting, I think it's basically the size distribution of the material that is entrained into the lower mantle of Earth. And I know that with SPH modeling that it's going to be really hard, even at high resolution like you have done, it's going to be very hard to understand what the size of the blobs or the size of the material from Theia that would be down here. Do you have any other methods for discussing what the expected size of the material, what radii would be?
Yes. Thank you, Robert. Nice question. As I briefly mentioned to you during lunch, so that's a critical comment raised by a reviewer. So right now, all SPH giant impact cannot receive resolution smaller than 10 kilometers in scale. That means your scale of the blob must be larger than that. But in principle, it can be smaller. So we made an argument that it can be smaller, even centimeter scale, but as long as this blob won't get evenly distributed in the mantle. So that means it may form a cluster structure. So in that way, it will get contamination with the Earth's mantle. So that will dilute the density contrast. But at the same time, you increase the volume. So volume is actually very important for Stokes sinking velocity. The volume is scaled with a cubic scale. So if you dilute a little bit density, if you have larger volume, you can actually sink faster than that. And also for one of our giant impact simulation, we have used a machine learning to see if there is a cluster train for this particle. We found it won't be evenly distributed. So as long as it's not evenly distributed, I think it can work. And also I gave a talk at Stanford. So Norman Sleep also helped me to answer one of these questions because we have the asteroid belt. We know the majority of the mass is dominated by large pieces. So as you can imagine, for these pieces, the scale and the size frequency should be comparable to that as well. So in that way, you will expect the majority of them should be large rather than small. So this is one argument, but I didn't know that before, but it kind of also makes sense. Yeah.
That's a fascinating idea. I think I'd push back on fragmentation through like collisional fragmentation compared to the material that is entrained into a body. It's hard to understand that the fragmentation laws would behave the same and that the distribution would behave the same, but it is at least a starting point. It's going to be very hard. I think it's going to take some time with our code to be able to resolve clumps with enough particles to understand what the actual distribution is. But for now, yeah, your particle size is around that radius, and that's a good start.
Yes, and also I have to say, although our model only consider canonical giant impact, so it's the energy release is rather smaller compared to the sub-Earth model. But I think in sub-Earth model, it's also principle to form this heterogeneity, because although that will melt the whole mantle, but these two liquids won't be the same. So and also the impactor will be larger, 4 times larger than the canonical model. So as long as mixing is not 100%, you will end up with some heterogeneity. That may be still enough to form these heterogeneities. That's my opinion. I haven't done any kind of this simulation, but I think it's possible, yeah, because it has larger mass for the impactor's mantle.
Other questions? There's one in the back.
You mentioned some geochemical work for the moon that was based on the neon isotope ratios.
Yes.
I was wondering if your kind of model of these being signatures of Thea would have any implications as to what the mantle of the moon should look like.
You are saying the major element or trace element?
These neon ratios.
Oh, neon isotope.
So you like?
Yeah. So I would try to say, in canonic model, 80% of the moon was made from Thea, and in our model is help a little bit. 50% of the moon is made of Thea. I would expect in the interior maybe 50% of the moon is similar to the Thea. Yeah. If there is no substantially mixing during the moon's internal processes. Yeah. Because the moon should have magma ocean, but we don't know how deep for that magma ocean and what's the mixing extent. So, but I think you still, yeah, I think it's possible to still find large Thea signature in the interior of the moon.
Have you attempted to model the circulation that would exist in the moon, like convection within the moon, and see if that has any effect on kind of, I don't know, distributions?
Okay. Nice question. So there are some, I was talking to Jeff this morning. He has a collaborators in Beijing, in Peking University. They are working on using manifold convections to study the moon's evolution. Most of my work still focuses on Earth so far. So maybe in the future, I will try to run some model as well to make consistent with my model. Thank you.
I have one more question, just regarding non-canonical impact or moon-forming models. I would like to see. It'd be very interesting to know whether the LLSVPs can still be described through this method in, say, a hit-and-run scenario.
Yeah.
Or ASVAG has some other options for moon-forming scenarios. There are ways to explain at least the angular momentum problem. If it's a hit and run, then a majority of the mass angular momentum could be carried away by leaving the system. So some of those problems are not as drastic as they appear. But the Synestia model, of course, has to invoke a very difficult dynamic to sap the angular momentum. So, but it'd be very nice to know whether other models can still produce this LLSVP signature.
Yeah. Thank you for the clarification. And I'm happy.
So I had a question just from a geosciences point of view. Does this model help explain anything about the low seismic velocity provinces that wasn't well explained by our previous models, or were those previous models still good and this is just a way of explaining the origin of the moon?
Okay, thank you. Nice question. So as I summarized at the beginning right now, there are two popular origins for the explanation for the blobs, one by subduction ocean crust. So these may have the potential, but as I mentioned, it has a limit capability to form large structures. So in our model, we can provide large amount of different materials very, very quickly. So we don't have that problem. For the basal magma ocean, idea is it has been very, very popular. But it's also kind of, I'm not sure if that model is also consistent with the neon isotope, but it's consistent with some other geochemical signatures, and they also, but as I argue, the basal magma ocean started with a whole depth magma ocean. But right now we have run giant impact simulation. If it happened in a canonical giant impact simulation, it won't have a basal magma ocean. So yeah, that's a difference between that model and our model. Yeah. Thanks.
I think we have to let people leave if they need to, but we can take more questions.
Did you track the iron material, the core material of the at all?
Nice question. I'm going to ask you during the lunch because no one still have trying to argue that T as core may explain why can deliver to the moon and can explain some cerebral elements on the moon as well. So they can track, but we didn't track. And also interesting, before I contacted them, they only tracked the materials in the lunar disk. They never tracked the material in the interior side of the Earth. Yeah. So yeah, the target is actually very important. I think it's very interesting to track.
Oh, so the impact models you were working with have been done for a previous study, and you were now tracking the material separately.
So my two or three of my co-authors, they only care about the lunar disk. Yes. They only care about the outer ring. They never want to see how you end up in the interior. So until I reached out to them, asked them to track that, then they found there are 2% impacted mantle in the lower mantle, which we were all very excited about that. So they haven't tracked about iron, but I think for your research question, I think it's very, very important.
Yeah, it'd be
important, very helpful.
It'd be important for the HSC development. Also,
yeah,
as we were talking about, there's also the ultra low, the UL SPZs, which are potentially even may have some iron material in them as well. Which could be part of this story.
So ULBZ, is also very interesting phenomenon, and yes, absolutely.
Yeah, I should have had people.
Thank you.